all life depends on a single thing: oxygen. So what happens when there simply isn't enough? Energy fades, and every breath delivers less than it should. High in the Tibetan Plateau, this problem gave rise to one of evolution's most remarkable stories, a story that is still unfolding today. The Tibetan Plateau rises nearly 3 miles above sea level, a world of mountains and endless plains that seems to float above the clouds. But there's a problem here you can't see. For newcomers, the symptoms show up fast. Breathing gets harder, simple movement takes more effort, fatigue hits sooner than expected. The obvious guess is not enough oxygen, but the air up here has almost the same percentage of oxygen as anywhere else on Earth. The real culprit is pressure. At sea level, the air around us is compressed by the weight of the atmosphere above. Oxygen molecules are packed relatively close together. High in the mountains, air pressure drops dramatically. The air expands and becomes much thinner. Every breath still fills the lungs with the same volume of air. But that volume contains fewer oxygen molecules than it would at sea level. That's hypoxia, and every creature on the plateau has to deal with it. How do you keep a body supplied with energy when every breath delivers less fuel? When oxygen levels fall, the body responds by producing more erythrocytes, the cells responsible for transporting oxygen through the bloodstream. At first, that helps. But the longer it goes on, the more it costs. Blood gets thicker, harder to pump, and the heart has to work overtime. The other part is the body's own adaptation. For millions of years, all life in the highlands has faced the same challenge. Yet evolution found not one answer, but many. To understand them, we must first understand how this world came to be. Today, Tibet is called the roof of the world, but it wasn't always this way. Millions of years ago, the ancient Tethys Ocean covered this region. Then the Indian continent slammed into Eurasia, and layers of rock buckled and rose. That's how the Himalayas were born. As the plateau climbed higher, the environment turned brutal. Colder temperatures, longer winters, thinner air. And yet Tibet didn't stay lifeless. It became home to animals, plants, and eventually people. For thousands of years, Tibetans have lived on the plateau despite its thin air. The obvious question was, how could people live their entire lives in air that contains so little usable oxygen? When scientists studied their physiology, they found something unexpected. Remember the mechanism we discussed earlier? When oxygen becomes scarce, the body normally produces more red blood cells. In Tibetans, that response is much milder, thanks to a gene called EPAS1, which keeps the body from overproducing red blood cells in the first place. So where did this unusual gene variant come from? The answer was a twist nobody expected. Tibetans appear to have inherited it from the Denisovans, an ancient human group that lived across Asia tens of thousands of years ago and interbred with the ancestors of modern Tibetans. Almost all of that ancient DNA eventually faded away, except for one extraordinarily useful adaptation, which thousands of years later helped humans survive in one of the most oxygen-starved places on the planet. Humans were not the only inhabitants of Tibet forced to adapt to life in thin air. Mountain dogs faced the same challenge. For centuries, Tibetan mastiffs and Himalayan sheepdogs have lived and worked at elevations where oxygen is never enough, herding livestock and covering huge distances, while other breeds would be gasping for air. Scientists found changes in the same oxygen-related genes, including EPAS1 in these dogs. But the story may go even deeper long before these mountain breeds appeared. The Tibetan wolf had already spent thousands of generations adapting to life above 13,000 feet. Some researchers believe that ancient interbreeding between wolves and dogs may have passed some of those beneficial traits into high-altitude dog populations. The idea is still being investigated, but the parallel is striking. Earlier, we saw how Tibetans may have inherited their advantage from the Denisovans. The same story seems to have played out again, this time among animals. Evolution didn't build something new. It borrowed what already worked. The Himalayan yak took a completely different route. Rather than fine-tuning a single gene, it rebuilt the entire pathway that oxygen travels through the body. That journey begins in the lungs, which are far larger than those of ordinary cattle and housed in a chest broad enough to hold them. From there, a circulatory system adapted to thin air delivers the oxygen deep into the body, where the yak's tissues wring more energy out of it than most animals could. No single one of these traits would be enough on its own. What makes the yak extraordinary is how they work as one system, each adaptation supporting the next. The result is an animal that thrives year-round at elevations where most large mammals would barely hold on. Life on the Tibetan Plateau is defined by its winters, long, bitterly cold, and stripped of food for months at a time. The air itself turns against you at this elevation as well. A body can draw slightly more oxygen from the air in summer than in winter. For a warm-blooded animal, simply staying alive through such a season demands an enormous amount of energy. The marmot's solution is hibernation. What happens next lasts more than half the year. The marmot's heart slows to a fraction of its normal rhythm. Its breathing fades to something barely detectable. Its body cools toward the temperature of the burrow around it. Energy use collapses, and with it, the need for oxygen. Month after month, it lives on the barest trace of what it once needed. Sometimes the best way to survive a shortage is not to increase supply. It is to reduce demand. The bar-headed goose chose a different strategy. Where others evolved to endure thin air, it evolved to perform in it. Twice a year, these birds cross the Himalayas. The air there holds only a fraction of the oxygen found at sea level. Their wings beat without pause, hour after hour. No single adaptation could carry an animal through that. So the goose improved every step of the process at once. Its lungs take in more oxygen from each breath. Its blood grips that oxygen more tightly than ours can. Wide networks of tiny vessels run deep into its flight muscles. They carry the oxygen straight to where it's needed, and inside those muscles, the cells convert it into power, wasting almost none of it. The yak rebuilt the machinery for living in thin air. The bar-headed goose refined it. From the first breath high above the Himalayas to the mitochondria driving each beat of its wings, the Himalayan vulture took the boldest shortcut of all. It didn't redesign its body at all. Instead, it learned to use the mountain itself. As wind rushes up steep slopes, it creates powerful updrafts, and the vulture simply rides them, gaining altitude with barely any effort. Less effort means less oxygen needed. While other species were rewiring their lungs, blood, and metabolism, the vulture just changed its behavior, and that worked just as well. At the start of this story, the challenge seemed simple. How do you survive where every breath delivers less oxygen? But Tibet shows that survival was never about finding one perfect answer. Different species found different paths to the same finish line. The same obstacle, it turns out, can produce an entire toolbox of solutions.